Welcome to the Space Telescope Public Lecture Series. Tonight, celebrating NASA's 40-year legacy of infrared astronomy from space with Dr. Robert Hurt of Caltech IPAC. I'm your host, Dr. Frank Summers from the Space Telescope Science Institute. And as always, I thank the wonderful tech team, Thomas Marufu and Grant Justice, who get these webcasts out to you. And I will note for the last time, because I'm doing it all of 2023, that the Space Telescope Public Lecture Series is now permanently online only. So you will not be able to come into our institute and watch it. It'll always be online from now on. Next month, on January 9th, 2024, Failed Stars and Errant Planets by Elena Manhavakas of ESA and the Space Telescope Science Institute. On February 6th, there will be a wonderful speaker with a fascinating topic. I just haven't scheduled it yet, but I will. I always do. And on March 5th, we will be talking about the April 2024 total solar eclipse. And we have several speakers lined up, but exactly who they're going to be hasn't been decided. But we will definitely get a talk in about that total solar eclipse before it happens in April 2024. To find out about such matters, you can go to our website, www.stsci.edu/public-lectures. And you will find this webpage. On the left-hand side, you will see links to our webcasts, both on the STSCI webcasting site and on our playlist on YouTube. And in the lower right, you can see how you can sign up for our occasional emails. Basically, you get about 2 emails a month reminding you of these talks, and you simply enter your email address in the box and hit the subscribe button. Also on our webpage are the lists of our upcoming lectures, and if you click on a lecture for the read more, you will find the description of the lecture, as well as after it's been recorded, links to the Space Telescope webcast, as well as the link to it on YouTube. For email, as I said, the announcements, it's easiest just to sign up at our website, but you can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. And if you sign up there, and you will get notices of our new videos and reminders of our live events such as this one. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. Our social media run out of the Office of Public Outreach. We do social media for the Hubble Space Telescope, for the Webb Space Telescope, and for our Institute on Facebook, X, YouTube, and Instagram. And I myself do a tiny bit of social media on Facebook, X, and I just started on Blue Sky because I got an invitation. I said, what the heck, let's try it. Okay, so I'm now drfranksummers.bsky.social. We'll see how that goes. All right. And now our news from the universe for December 2023. Our first story. What does tellurium tell us? All right, so this is a story about the event known as GRB 230307A. All right, so GRB stands for gamma ray burst. And what is that? Well, it's a big burst of gamma rays that we see in the sky. Okay, sometimes we astronomers were pretty straightforward. Gamma ray burst is a burst of gamma rays. 230307 says that it occurred on March 7th of 2023. Okay, so this event was the second most powerful gamma ray burst seen in 50 years of observations. We've been looking and detecting gamma rays for 50 years. This was the second most powerful ever observed. It was seen first by the Fermi Gamma Ray Space Telescope, but also by several other space telescopes, including, which is really cool, including a gamma ray instrument on Mars Odyssey. Yes, this gamma ray burst was seen on Mars. That's really cool. All right, and so you can see the red glow here. This is an observation from the Webb Space Telescope, and this is the mid-infrared glow as observed 1 to 2 months after the gamma ray burst went off. So there's still a remnant glow 30 and 60 days after the gamma ray burst. Now this may look kind of faint and everything, but remember, this is 900 million light years away. Okay, another cool thing about this gamma ray burst is that it actually occurred 120,000 light years outside of the host galaxy. So obviously this got gravitationally ejected from this galaxy, travels for millions of years across intergalactic space, and then goes off as a kilonova. And then you, of course, ask, well, what is a kilonova? I'm glad you asked. A kilonova is a neutron-star merger, when two neutron stars spiral around each other and merge together. And that is those neutron stars spiraling together, crashing and creating this big blob. All right. When that happens, when the two neutron stars merge together, they create a tremendous amount of energy, and that's what creates that gamma ray burst that we saw. It also creates enough energy that it can create new elements. Okay? So this is how astronomers view the periodic table of elements. Okay? Up at the top, there is hydrogen and helium. This is stuff that was created in the Big Bang, okay? Just hydrogen, helium. That's all we had after the Big Bang, okay? And then the yellow stuff and the green stuff and the blue stuff, the light blue stuff, okay? These are elements that are created when stars die, okay? Low mass stars blow off their outer layers and they send elements out into space. Higher mass stars explode and blow up, and they send elements out into space. But the heavier elements, the ones in orange here, those elements are understood to be created by emerging neutron stars. So when neutron stars merge, they actually make a significant number of elements in the periodic table. And tellurium, element 52, as you can see here, is one of those elements created by neutron star mergers. And so when we see a kilonova, and if we can get a spectrum of it, we can look to see what elements we find. And the Webb Space Telescope was able to get a spectrum of GRB 230307A. And there is a signature line here between 2 and 2.5 microns that is matched by a line of tellurium. So, what does tellurium tell us? Well, in this case, tellurium is showing us that our ideas of how you create many of the elements of the periodic table are being verified, because these, of course, are based on theoretical calculations, okay? We actually have to have observations to confirm them, and here is one of those observations. And we're watching the formation of tellurium in an object 900 million light years away. Our second story, Hubble and Webb create a panchromatic view. So color film came about in the 1930s. The Eastman Kodak company introduced Kodachrome in 1935, and it was an incredible advance in photography. All right, it allowed you to actually do color, and they improved it over the years and such, and they kept calling it Kodachrome and everything. And it had such an effect on the field that competitors, when they released their color film, they used names like Agfachrome, Ansochrome, Fujichrome, and Eastman Kodak's own Ektachrome. So this was such an important thing in terms of the color photography field. Now, in astronomy, we don't necessarily think of colors as we think of the wavelength coverage. And here in this diagram, we're going from the ultraviolet, which are shorter wavelengths than optical. The optical, the visible light that the human eye sees, into the near infrared, the mid infrared, and the far infrared. Okay, and so this is a broader spectrum than just what Kodachrome can cover. All right, and Hubble Space Telescope actually covers from just in the ultraviolet through the optical and a bit into the near infrared. Whereas the James Webb Space Telescope, well, it starts at the far end of the optical, goes through the near, all the way through the near infrared, and well into and through the mid infrared. All right, and so if you wanted wavelength coverage, you wanted all the colors that are out there, whether the human eye can see them, wouldn't it be cool if you had Hubble and Webb combined into one? Well, that's what we've done. A few years ago, as part of what's called the Frontier Fields Project, Hubble took this image of the galaxy cluster MAX 0416, okay? And this is one of the largest galaxy clusters in the universe, and there's all sorts of cool details in here, especially gravitational lensing details, all right? And so one of the projects to do was to follow this up with Webb observations and extend the range of our view of this cluster. And this was put together into an image. So here is Hubble alone, and here is Hubble plus Webb. Optical, optical and infrared. And you can see how much more we get when we're able to combine the two. This is panchromatic, working from the visible all the way up through the mid-infrared. And you can see that when I blink back and forth to the Hubble and then the Hubble plus Webb, how those red objects burst out, okay? Well, of course, in this color scheme, they're only seen in the mid-infrared, and Hubble, of course, doesn't cover the mid-infrared. So they definitely are shown there. However, the blue stuff, well, those blue things, well, they're there in Hubble, okay, because they're down at the blue end of the visible light spectrum, and that's definitely not where JWST can handle. So by Hubble covering one end of it and Webb covering the other, and they sort of overlap a bit in the center, we get a lot more information about these objects. Matter of fact, this is what we call the compass image of it. And down bottom here, it specifies the different filters that were used. There were 7 Hubble Space Telescope filters and 8 James Webb Space Telescope filters, so a total of 15 filters. Although I gotta say that the last 4 Hubble filters sort of overlap with the first 3 NIRCam filters, so there's sort of like 8 separate band passes that are put together. But the cool thing about this is it goes from about 400 nanometers to about 4 microns, okay? That's a factor of 10 in wavelength. So we'll really get a huge panchromatic view of this galaxy cluster. And I have dubbed this Webblechrome, okay? Webb and Hubble, Webblechrome, and that is the new definition of panchromatic for the future. All right, our speaker tonight is an old friend of mine. Gosh, Robert and I have known each other for at least 20 years, maybe, yeah? Something like that.
I think this might be our 20th anniversary of knowing each other.
Could be. In terms of the AstroViz meeting we had here
workshop
at Space Telescope. Anyway, so Robert is a wonderful person, and as I like to say, he's one of the few people in the world who also deserves the title of astrophysicist. So he has been out at IPAC for 27 years. Started out working in data processing and other things, and moved to science visualization for 20 years. And in his science visualization, he was doing a lot of data visualization at the start, but he's a hell of an artist, okay? He's been doing astro art since high school, so he's moved a lot to illustrations and 3D visualizations and such. We had the pleasure of working together on the IMAX film Hubble 3D. We worked on a whole bunch of projects recently in the NASA's Universal Learning AstroViz project and AstroViz Community of Practice. So we have a lot of fun doing that stuff. He is probably most known for the plan view of the Milky Way galaxy. So looking down at an artistic illustration of what the Milky Way looks like from above. And it's always fun to note that he drew that just as an illustration, and then people started taking it seriously. So he had to go back and revamp it to make it actually more scientifically meritorious. So I remember that you're commenting on that. I was like, oh, oops, I'm almost too popular for things like that.
And I will say that art had at least 3 artistic hypotheses that have since been borne out by observation that were verified in data. So
I love it when visualizations, improve the science, which that they do more often than people think. Let's see. He gave me a list of the missions he's worked on. Spitzer, of course, has been his main one, but he's also worked on Galax, New Star, Kepler, WISE, as well as various other ones for Caltech and NASA, including the black hole at the center of M87. Was it that you worked on, or was it the one at the center of the Milky Way? Or maybe both.
That was the Event Horizon Telescope Center.
Event Horizon, yes. Yeah. Okay. So I always like to say something interesting about him, and I have been to his place in California, and his living room is littered with models of spaceships. I mean, he's a fanatic at doing that. He has sort of a split affinity in his space. There he goes. He had to grab one, right?
I have several within reach.
Within reach. He splits his affinity between Star Trek, which is the space fantasy, and The Expanse, which is space fantasy that's really, really well based in reality. So, ladies and gentlemen, Dr. Robert Hurt.
Thank you for that introduction, Frank. I'll try to live up to that. Let's see. So start my screen share here. There we go. Hopefully everyone can see that now. So yeah, I'm here to talk about the 40-year legacy of NASA's investment in infrared astronomy from space, because it turns out that this year is an important double anniversary year, and that in fact our view of the universe in the infrared, and I'm going to focus not so much on the near infrared that Frank has pointed out, but the mid and the far infrared. It only dates back effectively 40 years, and that's the process of how we got from where we are now, from these early areas. That's what I really want to dive into, where we started to lead us to where we are today. Of course, where we are today, where we are today are the incredible images coming down from the James Webb Space Telescope, and that are peeling back the layers and showing us the infrared universe in detail that we've never been able to see before at this level. But it's important to note that this is not the first time we've ever dipped into the infrared universe. And in fact, science always builds upon its discoveries in the past to lead to where we are today. So when you look at a Webb image today, understand that this is the culmination of 4 decades of research that have progressively enhanced and refined our view of the infrared universe, dating back to 40 years ago this year, to the launch of IRAS in 1983. So just to set the context from a pop culture point of view, what was life like 40 years ago in 1983? Well, George Lucas had taken us to the end of the Star Wars trilogy, never to be seen again. Well, maybe not. Jennifer Beals showed us how to dance our troubles away, and ensemble cast in The Big Chill told us how to really deal with our 30-something stresses. And as far as computers were going, if you had a computer, which was not very common, you were likely storing your data on big 5 1/4 floppies that store data to the hundreds of kilobytes level. Yeah, it was technologically truly the dark ages. In fact, the 1980s, if you think about computing and supercomputing, the Cray 2 supercomputer that came about 2 years later, 1985, You would need about 5,000 of those top-end supercomputers to equal one of this year's smartphones. So just try to imagine one smartphone today could have revolutionized like every field of computational research 40 years ago beyond description. So this is the world that astronomy was operating in 40 years ago. By and large, the bulk of astronomy was being done from the ground, using large telescopes tuned to optical wavelengths of light, the visible light spectrum, and a little bit to either side of that. The primary data collection and storage medium for astronomical data was the glass plate, a photographic emulsion laid on a piece of glass, placed into the telescope and exposed directly to the light, manufactured by Kodak, in fact, in most cases. In fact, astronomy was the reason Kodak kept manufacturing glass plates for as long as they did to support some of the older observatories. And as such, astronomy images of the era when I was growing up were literally visible light photographs, often quite literally putting color photographic film into a telescope and letting it expose. So there was a sort of similarity, a common color palette that they all shared, showing us the nebula and stars of the universe. Talk a little bit about what it is and why do and did astronomers care so much at that point. Well, as far as the universe is concerned, there is no infrared visible, right? Light is just light. And the only distinguishing characteristic of light across what we call the spectrum is simply that it comes in a variety of wavelengths, from very short wavelengths to very, very long wavelengths. And that is all the universe really cares about. It is only humans that have a need to put naming conventions onto things where we divide the spectrum up into bits and pieces that seem like they're carrying a significance, but in fact, it's really just all about us, right? The visible light spectrum is merely that particular range of wavelengths that our human eyes operate in. In fact, it's not even a region shared by all creatures on Earth. Some can see into what we would call ultraviolet or into the infrared. Of course, when you get to longer wavelengths of light, that brings us into the infrared part of the spectrum. And this is actually all done to scale here. You can see that the full range of light wavelengths that our eyes can detect only differ by about a factor of 2, from the shortest blue and purples to the longest red wavelengths. But as you move out onto the infrared spectrum, you are now suddenly talking about factors of 10, even hundreds. I didn't even bother extending this out to 100 microns because, at this scale, it would just be like lines that would barely move, right? So the infrared spectrum really spans a vast range of the light spectrum compared to just that narrow range that we deal with. Now, in terms of what generates light and infrared light that I'll get to, there are a number of processes in physics, but one of the most fundamental ones is something called blackbody radiation. And this is simply the light emitted by matter due to its thermal temperature. It's a property shared by pretty much anything that's matter in the universe. And it's something that we have a lot of daily experience with. The glow of the sun in the sky is the sun's blackbody spectrum. The light from an incandescent light bulb or an electric burner or a volcano, lava spewing out of a volcano. These are all glowing due to their intrinsic blackbody spectra that are a function of their temperature. Now, of course, it turns out we too have blackbody emission. It's just not something that we think of because for humans, our blackbody spectrum is brightest in the infrared at wavelength our eyes can't see. But with the appropriate instrument, we turn into luminous creatures as well. So blackbody radiation is in some ways incredibly simple because it is a particular color curve that extends through the spectrum of light. And the shape of that curve is determined solely by the temperature of the object. When objects are very, very hot, these curves tend to go very bright and they peak at the shorter and shorter wavelengths of light. At the tens of millions of degrees, they actually peak in the X-rays, like around regions right around black holes. When you get into the thousands of degrees, then they tend to peak in the visible light spectrum. But when you drop to lower temperatures, to like 1,000 or under, then those blackbody peaks start to occur in the infrared. So in that sense, of course, contrary to art convention, blue is a hotter temperature than red, but red is a hotter temperature than infrared. So to turn this around into just more like a temperature chart, I've sort of laid out here the spectrum of light, and I've correlated it to the peak temperatures that you get from black body radiation. So in the ultraviolet, you're looking at the hottest stars. In the visible spectrum, you're getting to stars about the same temperature of the sun, around 6,000 degrees Kelvin, give or take. And not surprisingly, what the sun is most putting out in terms of light happens to be where evolution on Earth converged to create eyes that took advantage of what we had the most of. So in a literal sense, our sense of the visible spectrum is purely defined by the fact we evolved under a star that was around 6,000 degrees Kelvin. And so we use what nature was giving us. But you can get to, as you get to cooler and cooler stars, the peak of their black body spectrum shifts more into the infrared. You go further down, our body temperatures comes in about 300 degrees Kelvin. Astronomers, right? We always use Kelvin because that goes to zero, at absolute zero. Our peak infrared glow, thermal glow, is around 10 microns. And if you go out to even longer and longer wavelengths, the coldest temperatures in the Arctic are a little shy of 20 microns. And by the time you get down to maybe 100 degrees Kelvin, you're out at 30. Finally, you get to the very coldest things in the universe, at only tens of degrees above absolute zero. And looking around the universe, the cosmic dust that fills the spaces between stars, these are the kinds of things that get down to these incredibly low temperatures. So this is a thing that you can only access from the far infrared. And another aspect of these wavelengths is that these are locked off to us from the ground. That our atmosphere is transparent through the visible spectrum, and it starts to get choppy and harder to see through when you get through the near infrared, though you can still operate out to about 2 microns or so from the ground without too much trouble. But beyond that, you really need to move your telescopes, your detectors, outside of the Earth's atmosphere if you really want to be able to detect and see that light at all. So that is why, even back to the 1950s, it was clear if you wanted to do infrared astronomy, you needed to go into space. And the first mission that really opened our eyes to the wonders of the mid and far infrared universe was the IRAS mission, which was sent into space to cover these 4 bands that I've highlighted, ranging from about 12 microns out to about 100 microns. So this is its 40th anniversary year. It launched January 25th, 1983, so we're squeaking in just under the wire for it still being its anniversary. And while it only operated for 10 months, while it still had liquid helium cryogen, keeping all of its equipment nice and cold, so it'd be very sensitive to infrared emissions, it was able to provide for us a map of the sky. I'll get back to the fact that it is a map of the sky, because that's not what we expected initially. But some firsts that you can associate with IRAS. It was the first infrared telescope in space. And as such, it was the first far infrared map of what the sky looked like. This was a frontier that really we only had a slight inkling of what was out there based on, launching detectors on rockets that would sort of arc up and down, and you had to sort of interpret what came on these data sets. But it also was the first all-sky survey of the universe taken from a space platform. Again, there had been some telescopes that went into space that looked in various directions, but the attempt to actually systematically map out the whole sky from a space platform, this was the first for IRAS. And another kind of aspect of that is the first digital all-sky survey, because up to this point, the all-sky surveys that we'd operated from were taken on photographic plates, very analog systems. I put a little asterisk by all-sky because it did miss a little bit due to a couple of glitches, but it got pretty close to an all-sky. So IRAS also was a very different era of technology. The IRAS detectors were really large, big pixels that were like big wells for incoming light. And they are not arrayed like a camera array. These were literally designed to sweep past things and watch as the variations of brightness changed. These pixels were aligned in the detector array so that each set of pixels covered 4 different bands of the sky. There were sort of 2 sets for the 12, the 25, the 1600 microns. You notice the pixels got fatter and fatter as you get to the longer wavelengths. That's because the telescope resolution is actually a function of wavelength. And if you have a single mirror, as you go to larger and larger wavelengths of light, your effective resolving power gets reduced as just a consequence of the properties of light waves. So you actually, at the longer wavelengths, didn't need such a small detector. You would build it larger because there was no way to resolve things so carefully. Now, the way that IRAS operated is that as it orbited the Earth, it would look outwards, away from the Earth, and scan its detector across the sky, one pass after another. And when the detector passed over a bright source, like a star, it would respond if that actually had some amount of emission in the infrared. It was like a giant chart recorder, effectively. And the only thing that IRAS was actually planned and designed to do, and really expected that it would be able to do, is this kind of strip chart recording, right? No one really had a clear sense of what the brightnesses of objects were in the infrared. So the IRAS mission was designed to go out in space, run itself like a chart recorder, and when you got little blips, you could sort of look at the baseline before and after the blip and figure out just how bright that particular object was at the 4 different bands that IRAS operated in. And its entire intended output was supposed to have been a beautiful catalog of objects in the sky, and that was it. But there was a little more going on with IRAS. In fact, you notice in these strip charts, you see like the point source that pops up in these things, but you notice that there's like a lot of wiggles and drift in the background. There turned out there's a lot more going on in the sky than we thought. But let's go back. What can you just get from the strip charts? What can you just get by measuring individual objects? Well, one of IRAS's fundamental discoveries was that there were stars that were otherwise thought to be normal standards in the sky that possessed what we called an infrared excess. Now, this is something we take as second nature, honestly, in astronomy research today, but 40 years ago, this was an unexpected, brilliant discovery that something like a normal star in the sky like Vega, when seen in the far and mid-infrared, had an extra little bump to its spectrum, separate from the temperature of the star itself. Well, what would that bump be caused by? The interpretation is that that bump meant there was something else in the system that was absorbing some of the light from Vega, heating up and re-radiating it in the infrared. And that was taken to be evidence for debris disks, regions of where asteroid fields might be with ground up fine dust, filling out bands within the system, things that you would never see in visible light. And in an era, but when it was really unknown whether there were even planetary systems around other stars, this was one of the first clues that there may well be planets around other stars. Because where you have asteroid belts that grind together and generate dust that can be seen in the infrared, you might also have formed planets that might not be detectable yet. In fact, it was this discovery around Vega that motivated Carl Sagan to place his wormhole switching station in his novel Contact, later in the movie, in the Vega system, because Contact was only published a couple of years after the IRAS mission. And so this was hot news that there was something interesting going on in Vega. And so, as any good sci-fi writer would do, he used that science to enhance the story that he was telling. So another kind of infrared excess that IRAS discovered was infrared excesses in galaxies. And in many ways, these were far more dramatic than the excesses in stars, because it looked at some galaxies and found that there were galaxies that were over 100 times brighter in the infrared than they were in visible light. That you would look at these things and you'd see these swirling objects, and in fact, you were missing 99% or more of the energy because you weren't looking in the infrared yet. And this opened up, again, something that is kind of accepted and taken for granted today, but made us realize that there were these incredible energetic sources in galaxies, whether it be the bursts of star formation at a prodigious level, hundreds or thousands of times more than you see across the entire Milky Way, or that there were regions around central black holes that were generating such incredible energy output that was getting absorbed by surrounding dust clouds and then re-radiated out into the infrared. These were the clues we needed to open up this entire range of understanding active galactic nuclei, supermassive black holes, and prodigious star formation. And these things now are just standard operating procedure in the universe. But yeah, that was just these two discoveries of a slight or a lot of excess once you move out of the comfortable visible spectrum, right? Changed astronomy research and our view of the universe forever. But there was more going on to our view of the universe. Like I said, the original data product was supposed to just be these catalogs, and they were important. But the engineers and scientists working on IRAS realized there was a lot more information in that data set. And in fact, these wiggles in the baseline that were showing up in all of the bands were telling them something absolutely unexpected. There seemed to be not only hidden little rings of dust around stars or in the cores of galaxies, but dust that was filling our Milky Way in ways that no one had anticipated. And from these data sets, these strip charts, applying really clever engineering to a data set that was never intended for this purpose, the people working on IRAS over the time discovered they could start to use these strip charts to create actual images of the sky in the infrared. Now, I really want to drive home, right? This was never part of its design. It was never part of its plan. It was never something that anyone really had even imagined would be possible, in part because before IRAS was launched, no astronomer was expecting that our galaxy was filled with diffuse clouds of thermally glowing dust. This, at the time, got dubbed the infrared cirrus, because these were very wispy light clouds that were so pervasive and thought to be impossible because any dust at that temperature would be destroyed in these regions, or would be too far away from stars to actually ever be warmed up to the point that it would glow. In fact, one of the mechanisms for the infrared cirrus, and thanks to George Liu for our director today for a conversation, reminded me that one of the mechanisms that was not anticipated was an individual dust grain. If it absorbed just a single stray photon of light, that could be enough to excite it and warm it up to the point that it could radiate in the infrared. And no one was really thinking about some fraction of the grains will just happen to absorb a photon at a moment, and that's enough to light it up. So this transformed our view of the Milky Way and eventually led to IRAS creating our first all-sky infrared map of our galaxy and the universe beyond. And this map was, again, fundamental. In many ways, it's akin to the early maps of the Earth, where we finally saw how the continents were laid out, and that it would stimulate our sense of exploration, of wanting to understand more about the geography of the world. This, however, was opening up the geography of our galaxy. We saw a really bright glowing region right the dead center of our galaxy. We saw that the disk itself was glowing luminously and that dust filled regions, and we were seeing all the way through to the other side. There were individual regions we could pick out. The Rho Ophiuchi region, that was the first animation I ran, that stood out as just above the galactic center. The Orion Nebula is the little bright dot, lower bright dot on the right side there. Even the largest galaxies could actually be resolved by IRAS, the Large Magellanic Cloud to the south, and even the little blip that was the Andromeda Galaxy. So our first attempt to map out the way dust was distributed in other galaxies outside the Milky Way. But it also told us things about the geography of our own solar system. You might have noticed this blue band that arcs through the image. Well, that is a region that was glowing brightest at the shorter wavelengths, the 12 and the 25 microns. And that was the dust that we knew to be inside of our own solar system, being heated by the light from the sun. This dust was very much so the infrared excess that our sun would have if it had been viewed by an alien IRAS satellite 100 light years away. And this was the how the dust in our solar system was distributed, its scale heights, and what directions it was brightest at. So the question is, why does the infrared picture look so different than visible light? And this comes back to some interesting properties of dust and how it appears. One part about dust and the infrared has to do with the way dust particles interact with light of different wavelengths. So when you have wavelengths of light that are a lot shorter than the size of the dust grains are impenetrable. They get absorbed or scattered or reflected, and so the dust becomes a completely thick, opaque cloud that no light penetrates through. So when we look out in visible light, as soon as we run into a dust cloud, that's it. If it's dense enough, we don't see anything of the universe beyond that point. Whereas if the wavelength of the light gets long with respect to the size of the dust particle no longer becomes an obstruction to it, and the wave can easily just move around and through and pass beyond it. So the dust particles become transparent in the infrared. So the first difference in that image is the fact that the dust that obscures our view in the visible light simply becomes transparent and lets us see clear through to the other side of the galaxy. But the other thing that's going on has to do with the blackbody radiation curve of dust that I talked about before. In visible light, the dust is too cold to create any appreciable amount of glow. So it is simply opaque. It blocks our views of the stars behind. And the stars themselves are incredibly bright, but they're also very, very tiny. They're pinpoints spread through, made visible simply for the sheer scale of their luminosity. But as you push into the infrared, stars become orders of magnitudes fainter. And because they are so small, their cumulative light actually becomes really, really minor and is much less prevalent in the mid-infrared and practically gone at the far infrared. Whereas the dust, even though the glow of cold material is very faint, we are now at the peak of its emission, and we are both seeing through the dust. The dust is spread out over a huge area, spanning light years, and the light adds up from one dust cloud to the next. So taking these two factors together, what we see in this infrared view of the sky is the sum total of all the structures through the galaxy, the nearby ones spanning further above and below, off into the distant far edge of the Milky Way scene, all added up. So it gives us almost an X-ray, infrared X-ray through our galaxy, and we see everything that is hidden from us in visible light. So it's a good moment to maybe just talk a little bit about where I work, which is IPAC, which in many ways you could think of as the first Space Telescope Science Institute, because it is a center that NASA set up on the Caltech campus to be in charge of the infrared processing and analysis of IRAS data. We actually have two buildings on the campus, and IPAC served a very critical function because in those days, before internet, you just couldn't go and download the data. If you wanted to use IRAS data, you actually had to plan a trip, and you would come and visit IPAC. You would sit down with someone who would show you the tools, give you access to computers that could access the tape banks and load up the data sets you needed, and give you the support you needed to be able to study and analyze the data and use it to advance your science. So this was an era where it was much more hands-on and much more collaborative, right? You couldn't just casually interact with people across the sea. You need to go to where the data was and make use of it. It does sound like the dark ages today, but this is an environment where, like I said, our cell phone has tens of thousands of times more compute power than every computer in IPAC did back in the mid-'80s. Over time, IPAC's role actually expanded to include data archives, mission centers, and to support NASA's next great exploration of the infrared universe that started 20 years later in 2003. So let's run our pop culture ahead to 2003. What was going on there? Well, Peter Jackson had finished our run through Middle Earth, or so we thought, with the Return of the King. With X-Men 2, we were starting to get the slightest inkling of what a Marvel extended superhero franchise might look like. And Pixar was making incredible computer graphics movies that were almost not imaginable in the early 80s, and still had not been bought by Disney, in fact. And the data that we were storing on CD-ROMs and on hard drives was measured in the hundreds of gigabytes. So definitely more ability to cope with large data sets. And it is in this era that SIRTIF, the Space Infrared Telescope Facility, launched on August 25th, 2003. And this mission have now operated for over 16 years. This is the infrared view of the launch, because one of my jobs at the launch was I brought the infrared camera so that we could capture the launch of a spacecraft in infrared light, which you'll note has the interesting property that even that this was at night, how the heat of the exhaust lingered over time. Interestingly, Spitzer was launched on a rocket that looks a whole lot like the rocket that IRAS was launched on. Delta IIs. Spitzer was a bit bigger, so it was a Delta II Heavy. It was one of the largest payloads the Delta rocket's capable of carrying. But at a glance, you might confuse the two, because Boeing still used the same cyan blue paint on both rockets. Of course, SIRTIF came to be known as the Spitzer Space Telescope, and Spitzer had a lot of innovations itself that allowed it to study the infrared universe, not the least of which was that it was launched into space and left the Earth entirely. It was the first astronomical observatory that was sent away from the Earth. And this was because we wanted it to be in its own orbit around the sun so that it would be far away from the thermal heat source that the Earth represents. And so over time, Spitzer drifted further and further away from the Earth, following it in its orbit around the sun. So Spitzer had a lot of design innovations in it. And in fact, this had a lot to do with trying to find a way to make the mission cost effective by coming in at a fraction of the originally planned cost for the mission, and yet not sacrifice any of the science. So make it cheaper and make it just as good. That was the challenge. So for one thing, because it was leaving the Earth, it had to work without interventions, no servicing missions that were common for upgrading and repairing Hubble. In order to be reliable, it was designed to have only 3 single-point failure operations after launch. Compare this to over 300 that I understand James Webb had. One of them was ejecting a dust cover, one was opening a shutter over the instrument chamber, and one was opening a valve. As long as we cleared those 3, we were pretty sure it would be smooth sailing. So still a little bit of teeth gnashing, but far less stressful than to have 3 than 300. And what's amazing is that without any intervention, Spitzer functioned beautifully and nearly without incident for over 16 years until we concluded its operation in early 2020. And just as a sense of how far the technology had come for infrared detectors in 20 years, on the right we have one of the IRAS detectors for the 100 wavelength chip, and that was basically a single pixel. The IRAC array that was used for the mid-infrared work on Spitzer, which was a 256 by 256 array of pixels, was basically the size of 1 pixel out of the IRAS detector. So, obviously we were getting much better at building infrared detectors at this point. But the other innovation in Spitzer's design was that prior to Spitzer, infrared telescopes had been built in a very expensive, heavy manner by taking a pool of liquid helium for refrigerant and immersing the entire telescope and instrument chamber around this giant dewar. It was large, it was heavy, and it took much larger rockets to launch. So the challenge for Spitzer was, can we make it cold but use just a tiny fraction of the liquid helium that we're used to? So one of the things that made that possible was designing the spacecraft to be a passive heat pump. Every surface, now you see Spitzer has a cool dual tone thing. It's got black and silver, looks really rakish, I think, very, very stylish. But it's not just to look cool and rad, right? It's to be very functional. You'll see that every surface that faces towards heat is built out of reflective material that is insulating and reduces the amount of thermal absorption from the hot directions, the sunward directions. And then every surface on Spitzer that faced away from the heat sources towards deep space was painted like a Vanta black, one of these super blacker than blacks. And black coloring is the ideal surface for heat radiation. It is the optimal form for a black body radiator. And so it turns out that if you coat all of your outward facing surfaces in black, they will passively pour the heat out for you into the depths of space. And as a result, even in the absence of coolant, Spitzer could maintain a temperature in its instrument chamber at 30 degrees above absolute zero, even after all of the cryogen was exhausted. And this was critical because it enabled Spitzer to last as long as it did. This is a sort of mission plot of, with respect to the Earth, sort of keep the Earth and the Sun fixed, as the orbit goes on, how Spitzer drifted farther and farther away from the Earth over its orbit. And so the cryogenic mission for Spitzer lasted for over 5 years, just longer than anticipated through, again, some very clever engineering. And at that point, Spitzer's instrument chamber went from being able to being cooled from a few degrees above absolute zero to 30, which meant that one of its 3 instruments was still functional at full efficiency. And that began what we called the warm mission. 30 degrees Kelvin doesn't sound that warm, but to an infrared astronomer, it's on the warm side. And that warm mission extended over many, many years, past our 15th anniversary. There was actually a point in 2016 where we actually redubbed the mission name to Spitzer Beyond, simply because in order to keep operating Spitzer so that it could continue pointing towards Earth and downlinking its data, we literally had to override several critical safeties that had been put into Spitzer, constraining it from doing operations that might damage it. So we're saying, yeah, it's okay, keep doing that. But in fact, Spitzer, even through the Beyond session, operated without incident, collecting data and pushing many frontiers of science. Now, Spitzer was not an all-sky observatory like IRAS was, but as it still had time to do some extensive mapping. And by highlighting just the thin slice of sky that runs through the galactic plane, Spitzer made the most detailed survey map to date of our galaxy, the bulk of our galaxy. This is a little radar chart that sort of gives you a sense of geographically where the galaxy we're looking through. And then Spitzer, what you see here are the many, many layers of dust clouds extending through the disk of the galaxy further out. And even though there have been other sky survey missions, this to date will still be the highest resolution map of the entire galactic plane that we're likely to see for some time at these wavelengths. Now, of course, Webb will be able to pick individual areas and dive in incredible detail here. But the work that Spitzer did is going to set up and enable that science moving forward. So Spitzer did had a lot of discoveries over its years. I got to produce literally hundreds of images of infrared objects from stars and nebulas and galaxies. But I'll pick just a few science highlights that came from Spitzer's mission that were very noteworthy. One of the things that Spitzer did is made what we can really call the first thermal map of an exoplanet. By studying the glow from a hot Jupiter as it orbited its star and following how the total light of the system rise and fell over time, we were actually able to figure out where the hot spot of the planet was relative to its orbit around the star, and that in fact the hottest point on the planet wasn't the part right under the star but shifted a little to the side, which became our first opportunity to think about weather patterns and wind flows on planets that we can't even resolve individually with even a telescope as powerful as JWST. And I should also note that when it was launched, one thing that Spitzer was not designed to do and not thought to be capable of doing was exoplanet studies, because it simply wasn't built with the right precision. But through nothing more invasive than software updates, the Spitzer science and engineering teams figured out how to literally reprogram the hardware to compensate and give it an order of magnitude better pointing precision than it was designed to have, and to be able to measure the photometry off a single pixel on one of those detectors with such accuracy that we could actually characterize so carefully the small amounts of light, that the changes in light that come when planets pass in front of their stars, or more importantly, the glow from a glowing planet as it passes behind the star itself. So this is an example of software upgrades actually completely renovating the science Spitzer could do and made it one of the fundamental tools during its lifetime for characterizing exoplanets and sometimes even discovering them. Spitzer also discovered what we now know as Saturn's largest ring. It's only visible in infrared light, and it's very large, connected to the material thrown off from the moon Phoebe. But again, this would be, if we could see in infrared, we would see this thing bigger than the full moon in the sky. But again, only visible in the infrared. Another exciting thing Spitzer participated in was the Deep Impact mission, the collision with an impactor on Comet Tempel 1. And Spitzer's spectrograph was able to study the glow of material ejected after we smashed the probe into the surface of the comet. And from that, come up with what we call the recipe for comet soup, to basically understand the composition of materials in great fidelity that got ejected into space after that collision. Another fun thing that Spitzer discovered in studying the nebulas around dying stars, these planetary nebulas, Spitzer found evidence for the existence of buckyballs. This is something that to that point, had only been created in labs. These are lattices made purely of carbon atoms, and with collections either 60 or 70, that the C60s arranged in the shape of kind of a classic soccer ball design. But they'd been hypothesized to exist in these environments for over 20 years. But Spitzer was actually able to detect this very specific signature of both varieties, and thus confirming that this is a process that happens in the atmospheres of evolved stars. Of course, Spitzer's greatest discovery, I think, that will be remembered for, is identifying the 7 Earth-sized worlds of the TRAPPIST-1 system. Now, TRAPPIST-1 was discovered from the ground, but because of the way that ground-based photometry gets meshed up by, you can't observe when it's cloudy, you can't observe when the sun's up, you can't observe when it's too low to the horizon. We knew there were at least 3 exoplanets in the system, but it was confusing, the timing was off, and we couldn't really understand what was going on. But by taking Spitzer at the beginning of its Beyond mission phase and being able to dedicate 500 hours of unbroken observations, that became the Rosetta Stone for one of the most interesting planetary systems discovered to date. Because with that many planets orbiting around, you needed to be able to keep enough data to see the cadence of each different transit to basically extract out the makeup of the whole solar system, or stellar system. So much of the work that we will hear moving forward of TRAPPIST-1 was enabled by the discoveries that Spitzer made. So looking back now, 20 and 40 years, we see these were 2 major mileposts of expanding our understanding of what the infrared universe was. The discoveries that IRAS made changed and influenced the way Spitzer was designed and became the foundational reference point to plan Spitzer observations. In the same way, the science that Spitzer has done and the incredible data archives of its entire mission are tools that can be used to apply to James Webb studies and to help us understand how to use Webb to its best impact to find the most interesting answers, the most interesting questions that we want to answer. But they weren't the only ones, and I throw a few more here just for reference, that missions that NASA has at least had some involvement with. In 1995, the European Space Agency launched the Infrared Space Observatory, ISO. It had a much more scaled down kind of detector than Spitzer did later, but even with a 32 by 32 pixel array, it started to show what we would expect to map out in infrared. And so much of the science that ISO did was foundational for planning the first most interesting research projects that Spitzer would take on. Likewise, a few years after Spitzer's launch in 2009, we launched 2 other infrared missions. The European Space Agency's Herschel Space Telescope opened up the very far infrared sky for the first time at some of those at wavelengths beyond what even IRAS had done. And NASA launched the Wide Field Infrared Survey Explorer, or WISE mission, which was kind of a follow-on to the IRAS All-Sky survey. It didn't go out quite as far in wavelength, but it it mapped out the whole sky and is still actually functioning today, much as Spitzer did in a warm mode, repurposed to look for potentially hazardous asteroids. So this chart lays out some of the major infrared telescopes that have been deployed over the last 25 years. And I wanted to show this against the wavelength of infrared light, just to really tell the story of when you are working in the mid to far infrared, where you must be in space to do this work. The fact that each telescope brings to the table a different character, a different part of the spectrum, and that there are parts of the spectrum that we could observe when Herschel was operating that we can't observe anymore because Webb doesn't go out that far. There are capabilities that each telescope brings to the table, whether it's the ability to map a large region very efficiently, but maybe not at as high a resolution, or to delve in incredible detail in a very specific region, but not necessarily get the whole picture. Each loss of a telescope is a loss of a certain kind of capability, and we rely on those data archives for future understanding of our science and planning future missions. So for now, we can look towards what James Webb is doing in the context of the research that brought us to understand the kinds of questions we want to ask with James Webb. And in so doing, how James Webb, and just imagine the questions that James Webb is going to answer and then further ask that future generations of telescopes will take on. So I just encourage you to look at all of these missions over time and imagine what it's like at each stage, understanding each veil of the universe as it's lifted in the infrared, and how each generation of telescope will expand and deepen our understanding of the infrared universe. And on that note, I think I can say I have concluded.
Thank you very much, Robert. That was a comprehensive look at quite a wonderful history of NASA and ESA and everybody's exploration of the universe. One of the questions that always comes up especially when talking to teachers is, well, how do we separate between what's near infrared, what's mid infrared, what's far infrared, and then what's microwave, all these things. And as you said, the universe doesn't care. But we set it up, and usually it's like by detector technology is what I've found in a lot of that.
Yeah,
where do you think those go? Yeah.
Yeah, no, and that's exactly it. It's so often it gets determined by the kind of engineering you do to detect a certain thing. But the dividing line between far infrared and microwave, right? That I've tried to look that up before, and it's like, whose standard do you want to draw the dividing line? And it's interesting because on one hand, you build detectors to work in, say, even longer wavelengths, like fractions of a millimeter. You build them like little radio receivers, and yet you can also build things that work as like kind of like chip detectors, depending on the right semiconductors. And there's some overlap between these techniques, and so people tend to view it in terms of the context of how they do it. And another confusing thing is like when you get into submillimeter wave astronomy. Historically, that field, a lot of it talks in frequency units instead of wavelength units, and it's like completely confusing. Like I always had to do the translation when I was working with Herschel data, because they loved talking about the frequencies of these bands, because they were thinking like radio engineers building receivers. And it turned out the numbers were a lot neater when you translated them into wavelengths, but that's not how the engineers did it, and so often the press releases were working these different units. But I mean, the way I tend to work with the near, mid, far is sort of, I personally tend to clump near infrared into the stuff that you can do from the ground. And that's, for instance, why I actually left Hubble out of the conversation. Hubble goes into the near infrared, but fundamentally it's not covering the wavelengths that you couldn't also do from ground-based astronomy. It's not, don't get me wrong, it's done wonderful work. But my focus here was opening up the space-only part of the infrared spectrum. And so that's how I filtered and chose the particular instruments I used. the transition from kind of mid to far infrared, I have never found a good dividing line, though I think some people may simply do it by which type of semiconductors you build to be sensitive to one part of the spectrum and the other. And I've never been much of a hardware engineer, so I can't speak to exactly where those lines fall. But I figure the transition between mid and far comes somewhere between like 25 microns and 60. And I'll happily entertain dividing lines from the peanut gallery on that.
You're not going to get any arguments from me, but I will say that the other thing that confuses people is when we call it millimeter wave astronomy or submillimeter astronomy, and yet in the electromagnetic spectrum we call that the microwave region, etc. So we use a lot of different terminology. And I remember at one of the conferences I went to, somebody was talking about a few gigahertz or something like that. And he said, I like to call it the 3-inch luminosity function because the wavelength of what he was looking was so big. It was a 3-inch wavelength. All right. So it was great that you showed off some of your favorite observations from Spitzer and IRAS. The infrared cirrus and the zodiacal dust, are stuff that when we look back on it, we should really have expected that in terms of things. I guess we did anticipate the zodiacal dust on
the
that.
Zodiacal dust, I believe, was anticipated, but I don't think anyone had fully appreciated what a wealth of data that was going to provide. That suddenly having these strip chart measurements through it would allow and a level of modeling of that I think no one really had anticipated before IRAS launched. It was one of the many things, like IRAS was really built, and I was talking to colleagues to make sure I understood this. I was just in college when the IRAS was launched, right? This was, this stuff was stuff I was reading about in Science News and going, whoa, there are like cirrus dust clouds out in interstellar space. Blew my mind, and later, by the time I was in grad school, I started using IRAS data and using the techniques that they had developed to make, the highest resolution images possible out of the data sets. But it was amazing the degree to which, you design a mission for a very specific purpose. And IRAS was designed to get very good measurements of point source brightnesses. And they thought, there might be, a few hundred, maybe 1,000 or so galaxies that they could measure, and tens of thousands of stars. And the catalogs were just vastly larger than they had expected. I think 250,000 sources in the primary IRAS catalog, tens of thousands in the extended source catalog. Right? These numbers were just so much bigger because, again, before IRAS launched, right, the only information we had about the far infrared spectrum was off of things like sounding rockets, where you sort of put a forward-facing thermally sensitive detector onto the tip of a rocket and you fly it up as high as you can, and as it arcs across the sky, you get like one swath at a very big, fat resolution, and you're trying to disentangle all of this, right? We knew so little at that point, but there was
pervasiveness of dust in the sky was just astounding.
In fact, and the crazy thing is, I think there were people who believed the dust was out there, but they didn't believe it would ever be heated to a point that it would be detectable at those wavelengths. Mm-hmm. It was really this unexpected mechanism that you could have single photon chance encounters of one dust grain might absorb one photon and warm up for a little bit and then cool off, and another one nearby, the same thing. That cumulatively would create something that you could see. And the other thing is, when you get down to 12 microns, in that region, we're actually now also operating in a whole different mechanism for dust luminance, and that's this is where you have these polycyclic aromatic hydrocarbons, these long-chain carbon molecules, and those actually are lighting up by a completely different mechanism. That's like a fluorescence mechanism, where they're absorbing higher energy photons, and it excites spectral line emission that's like this weird mushed up cloud that looks very broad band, but it's really a bunch of different, very specific transitions that are all at slightly different energies. And so you get these very broad features. And that wasn't a mechanism that was even anticipated at that point.
And plus the fact that it's optically thin, so that you can see way much further than you would see in optical. All right, so Grant Justice has been monitoring the chat. We've had a bunch of questions and stuff coming through the chat. So Grant, will you join us and bring us some questions from the YouTube chat?
Absolutely. All right. So first off, let's get started with getting ourselves in there. What is the shortest length? Like, what's the most narrow you have been able to do your observations into the spectrum?
I'm not quite sure I understand.
Yeah, I'm not sure I understand that.
Okay, so everybody in the chat is talking about the difference between what it's capable of observing from from its microns. The question was, is there a JWST-like telescope, or is JWST capable of observing in the 1 to 500 micron range?
Yes,
so
right.
Yeah. What's next for the far infrared?
Yes.
There. That actually, that's a good question. I have not been following. There's nothing coming up soon for it. We have a decadal survey in astrophysics, and there were multiple proposals on the table on what we would really throw our efforts into as a community for the next decade post Roman. And one of them was a proposal for a far infrared telescope for the fact that there's a whole patch of the spectrum that is uncovered now ever since the end of the Herschel telescope, but that wasn't selected, and we're actually, I think it's refocusing on something more designed for studying planets and exoplanetary systems. But honestly, I don't think there's anything really on the table for far infrared universe for the foreseeable future, and that's why these telescopes and these archives are so precious to us, because we may not have any more data on far infrared light from star forming regions for decades.
Whereas the near infrared is actually getting a bounty in terms of Euclid and Roman that are going to do these broad surveys at high resolution in the near infrared. So the far infrared is a little neglected coming up.
Yeah, so really JWST is going to be the way to go right now, and it only gets out to the mid-infrared range.
Yeah,
but that's going to be
20.
Powerful and important.
Yes. Cool. Thank you.
Okay.
So, as we look farther back in time, when the universe was denser, and how does that affect the redshift, or is there even an apparent change in redshift associated with the apparent acceleration?
Sure. I mean, that's something that I didn't even get into when I was motivating why infrared is interesting, and that's an excellent. It's a whole other area. I always have to what am I not talking about this time? But the expansion of the universe, as you stated, results in light coming from distant sources astrophysically. Their light is literally getting stretched along with the expansion of space itself, and we see that as this cosmological redshift. And that's one of the reasons you do need to work in the infrared part of the spectrum if you want to push back to the distant universe, because things that would be visible light in a nearby object have actually gotten pushed to much longer and longer wavelengths. And as you go out to longer and longer redshifts, that is a measure of proportionally how extended the wavelengths have become. So if you want to study things at redshifts of 10 or 20, you need to look at wavelengths 10 or 20 times longer to get the equivalent phenomena. And so that's why any cosmology study is deeply dependent on pushing to longer wavelengths out into the mid-infrared.
Yeah, and JWST is delivering in spades on that. We're getting confirmed ones out at redshift 11 and 12, which would have been stunning back when I was in graduate school.
Yeah, I mean, 3 or 4 was really exciting back then, right?
Oh yeah. I took classes with Hai Spinrad, who set the record for the distant object observed in the universe several times during the 1980s. All right, so I'm going to ask a question that the folks in the chat may not think to ask. How long is it going to take Spitzer to go all the way around and Earth catch up with Spitzer? It looked like it was about 60 years from your diagram.
That good eye, actually. That I love this question because this was another thing that we actually didn't understand before launch or even after lunch. But when people started looking into like how is Spitzer's orbit going to evolve over time, and yes, so the baseline is about 60 years for Earth to sort of catch up to Spitzer's lagging. But what was interesting and not actually appreciated at the time of Spitzer's launch is that we will never overtake Spitzer, because it turns out Spitzer is in this very unusual kind of orbit called a horseshoe orbit, where basically once we kicked it off and it went into its own orbit, it gets to a point where as we start to catch up with Spitzer, Earth's gravity will begin to accelerate Spitzer just a little bit. And it will get to a point where all of a sudden Spitzer will make a transition from an Earth trailing orbit into an Earth leading orbit. And it will start taking off back in the other direction from whence it came. And so over the coming centuries, if you imagine watching, like just from Earth's perspective, keeping the sun fixed, right? Spitzer falls behind, catches up, speeds up, goes into a shorter orbit, and then leads the Earth, and then and back and forth. So it'll just sort of bounce back and forth for a long time to come and we'll never actually pass it directly. And it was crazy because the orbital dynamics folks, right? They hadn't really run the numbers on that until years later, and I think it was maybe by the 15th anniversary someone had finally realized, oh yeah, we will never actually fully overtake it. I was always hoping we would overtake it and then we'd grab it and put it in the Air and Space Museum. So.
Yeah, it's like those stellar box orbits within galaxies that we learned. I don't know if you learned about them in graduate school. They confused me in graduate school. I knew they worked. The mathematics of it worked, but sometimes the orbits of stars within galaxies were kind of funky to me. All right, Grant, what else we've got from the chat?
Sure. Two things first. One, I love the dichotomy of you being like, oh, that orbit looks like it's around 60 years and being dead on, and then in the next sentence being like, I didn't understand that thing from graduate school. Amazing. Second, the chat has asked me to let you both know that you're matching, and they love it. You are wearing identical shirt. Well, not identical, but they're in love.
Mine's special. I'm wearing.
I have no patch over here.
This is the this is the Spitzer Beyond shirt. This was we did a logo especially to commemorate that point where we were overriding the safeties and going into overdrive for the last stretch of the Spitzer mission. So, and the graphics that I actually came up with for the Spitzer Beyond, I actually had to design this one was. Since we had just started the TRAPPIST-1 observations at the beginning of the Beyond phase, that was sort of became the symbol for what we were achieving in the Spitzer Beyond. And while we that was certainly the most amazing thing that came out of that period, I will say the amount of exoplanet science and characterization follow-up was truly remarkable through the end of the mission when we finally shut it down.
I will say that the shirts weren't planned, but I did change my background to be the Spitzer view of the Lagoon Nebula so that I would have an infrared background for our infrared talk.
And I did skip over talking about extragalactic science a lot, so I decided I would throw up the Spitzer view of MAD-1 in the background to at least have it there in spirit.
I love it. So I actually have clarification on my question from earlier. Thank the chat. So the question before on redshift and the apparent change, he was asking about the change in spatial density on the rate of time. As we look further back in time when the universe was denser, he's talking about time being slower and that affecting the redshift.
Was he thinking there that there would be some sort of gravitational time dilation? In our observations, that there's not enough of that effect to change it on a cosmological scale. On an individual object scale, that's where you can get the gravitational time dilation, but not on a cosmic scale. Certainly on scales like that.
Yeah, that would have to. I mean, the equivalent velocities that we're looking at those distances, those redshift, aren't not even close to the order of magnitude of the speed of light. So. and you don't really see the time dilation until you really get up to like the 99 percentiles where you really start to get something measurable.
Thank you. I love these questions because a lot of times people don't know what to ask until they find out that we got to lead them somewhere. Yeah, myself included. So,
I will just say it's almost wouldn't matter because, you know, at the time scale that we live at as humans, pretty much every galaxy looks like it's frozen in time to us, right? Because the time scales of galaxy change are so slow anyway, right? You know, it's like the difference between that or a galaxy slowed down to 1/10 of its speed due to relativism. Yeah, it would still just look like a snapshot to us. So,
drop in the pan for us.
I had one more question I wanted to just probe a little bit further onto that Saturn dust disk because I hadn't appreciated that before you mentioned it today. That you're saying that's 30 arc minutes across or more.
Yeah, I have to actually look up the numbers offhand, but interestingly, it was actually hypothesized to exist because of the moon Phoebe. It was hypothesized that it might actually there might be material and debris kind of cast out from it, and so we couldn't ever look at Saturn because Saturn was way too bright for Spitzer. It would overwhelm our detectors. But that's why they planned an observation. Like, well, if it's going to exist, there should be some sign of it here. And when they looked in that section, like, woof, whopping bright thing. So we weren't able. It was sad that we never actually tried to map out as much of it as we could so that we could sort of have a picture. But we got one clear slice of it, and that let us know that it was absolutely.
Because that's what confused me is your observation that you showed was just one tiny little slice, and I'm like, come on, if there's something that's that big. So when Cassini was there observing Saturn, and we got that fantastic backlit picture of Saturn, and you can see the extra rings and everything, Cassini's probably still inside that disk.
Oh yeah, this is
much larger than all of Cassini's orbits and everything. All right, so Cassini couldn't see it because it wasn't like we're inside our Milky Way galaxy. It was inside of that disk.
Well, also, even so, it still wouldn't see it because this disk is made of particles that are soot black, and Cassini didn't have invisible light. That disk is just not reflecting enough light to be detectable at all. But those soot black dust particles actually warm up as they absorb light from the sun, and then they radiate out in the infrared spectrum.
So we need a mid-infrared satellite of Saturn to really study that in situ.
Yeah.
Okay, great. All right, Grant, we got one more question or two more questions?
Yeah, we'll do a question and then a quick follow-up. So from the chat, dust clouds. Can we distinguish between individual dust clouds, not just and knowing that we are seeing through more than one? How do we distinguish them individually? IR, locationally, based on composition?
That is notoriously difficult, and this is when you sit down and you take a picture of a panorama, like you're in a field, you take a photo and you say, oh yeah, I can tell those mountains are far away because they're disappearing in the haze of the sky, and I can tell how far away the trees are because the nearby trees are big and the far ones are small. We just don't have of through the galactic plane, the Spitzer survey through the plane, and you're seeing all these incredible structures. There's just not a lot of things we can latch onto that we can attach a particular distance to one particular clump versus another. There aren't really emission lines of blackbody doesn't have an emission line that has a particular wavelength. But we can do that for gas clouds. If we're studying gas clouds, we can measure the velocity vectors and their flow, and we can sort of do some things to figure out how far they are. But even then, it gets all just disentangling the shape of the Milky Way galaxy is a decades-long project that's nowhere close to being done. And there are whole regions of the Milky Way that even knowing the velocity fields doesn't help you because they're moving more or less tangentially to your line of sight, so you don't get any useful information. So yeah, it's a perverse that we have this incredibly detailed dust map through the galaxy, and for so much of it we literally don't have depth information. I think if you really wanted to do that, you need to take another Spitzer and send it out about 10 or 15 light years that way, and then do the whole map again and then do it stereoscopically. Then you put on your 3D glasses, and then you're like, whoa, then you would see the disk.
Yeah, I would agree with that. It's one of the things when we start looking at the map of our Milky Way galaxy on the night sky, recognizing that most of those dark clouds are actually relatively close to us. Because because we're slightly below the plane, and they're in the spiral arms near us. They look like they're out at the center of the galaxy and such. And so, interpreting the dust clouds even in visible light is quite difficult. And you look at the stuff behind me, and I'm like, how do you tell what the 3D structure is of that?
Yeah. I will say I actually was chatting with a colleague of ours, Alyssa Goodman, recently, and she's involved in the MilkyWay.org project. And one of the data sets that they've been playing with, and I actually was doing some visualization work on this because it's a really interesting data set for the nearby part of the galaxy. Now, this is nowhere near as far as most of what's in the Spitzer imagery. When you can still work in visible light and it hasn't completely blocked your view of stars behind it, they are using the Gaia catalog of stars to figure out what the dust structure is out to like 1,000 light years away. Again, this only doesn't work when the dust gets so thick you can't see through it, because then your knowledge ends there. But if the dust is this diffuse cirrus and it's just reddening and dimming the stars but not making them go away, you can actually use the fact that Gaia has the 3D positions of all the stars. Then you can figure out how much some of the stars have been dimmed, that you can sort of retro-engineer how much dust would have had to be in the different sight lines in order to do that. And then you do that, you can actually get this 3D map of where the diffuse dust clouds fall in the nearby galaxy. But again, like I said, that only works out to a certain distance, because eventually, especially when you start looking towards the center of the galaxy, you start running into so much dust, you're just not seeing stars anymore in a lot of the sight lines.
Yep.
And that's kind of where Roman's going to take over, right?
Yes, and going into the near infrared, just going out to 2 microns gets you through so much of the galaxy at that point.
So much more. But
Roman won't have the 3D positions of some of those stars, right? You need a Gaia to do the map. But I mean, again, Gaia was built to measure the star locations at both things, to look for the parallax. Roman has the resolution to do that. The question is, it has to have the time to do that, right? Because that's a huge survey. It's a lot of data. So you'll be able to do some of that. But yeah, it's an interesting trick to use. As you push further into the infrared, you can get further through the dust clouds. And if you still have enough reddening information, then that can really help you figure that out. But on the other hand, if you go too far in the infrared, then you lose all the reddening information. And so now you're not actually sure was there a dust cloud or not, because you're at wavelengths where it just passes through the dust entirely.
So to really do this, you're probably going to need a 2-micron Gaia.
Well, you're going to want it like a whole bunch of different wavelengths through the spectrum, and when does the light start getting reddened and dimmed? It's like that went further through the dust.
Then you're going to need yes, exactly. You get your next one, then you say, okay, we solved those problems. Let's move to the next one. Right.
You need to get enough that you get a little bit of reddening, but not so much that you can't see it at all.
Absolutely. All right,
Grant.
Grant,
fun question to end on.
Okay, go ahead. I'll let you go.
All right. What is your favorite observation that you have made during your years, and why?
Oh. So, okay, my favorite observation, it predates my work on Spitzer, but it was when I was in grad school. My thesis was studying a galaxy, and this kind of connects me to how connected I am to the infrared. I was studying a starburst galaxy called Maffei 2. It's a actually quite large galaxy in the sky, but it wasn't even known to exist until the late 60s, because it happens to fall behind all those dust clouds in the plane of the Milky Way. And so as a result, radio light goes through that. I was studying it in VLA data, radio data, some millimeter data, but I didn't know what the galaxy actually looked like from a stellar component until I actually had a chance to talk to some researchers at NOAO, now Noir Lab, and I was able to propose to go to Kitt Peak to do some imaging of that galaxy in near-infrared light. And that was long enough wavelengths to penetrate a lot of the dust. Not all of it. It was still obscured and reddened. But to basically get this clear image back of the near-infrared distribution and suddenly understand what the star distribution was in this galaxy, to connect to everything that I'd mapped out about where the gas was flowing and where the starburst was happening in the center, right? That really was like this moment of just revelation, you know, that pushing to these wavelengths let me see something that would have been called a Messier object if it had been at a higher galactic latitude. You know, I mean, this guy's 15 arc minutes across. It's not small. It would have been bright and incredibly well known. But because it was just that obscured, that really impressed upon me how you push to different areas of the spectrum and you can basically discover things were lost to you. So otherwise, so yeah, I still have a soft spot in my heart for the Galaxy Maffei too.
Astronomy wall hacks. I love it.
Yeah. All right.
Spitzer made a nice picture of it too. So.
All right. Well, thank you, Robert. Love your enthusiasm as always. Next month, January 9th, Failed Stars and Errant Planets, Elena Mahavakas. January 9th, we will see you then. Thank you all for listening. Thank you all for watching.